Welcome to today's class of analog microelectronic circuits. In the last class we started with unit 4 where we discussed about op amps. Just to revise, we have discussed about the limitations of a regular amplifier and what we are expecting out of an op amp. Out of that, some are very key features what we discussed, where the input impedance is infinity and op amp is not supposed to draw any input current. The output impedance should be as same as an ideal voltage source, where your output impedance should be equal to 0. And then later we saw that looking at the characteristics what we are looking for an op amp, the ideal features we have discussed as the differential gain, common mode rejection ratio, and bandwidth. So these are some of the features what we expect out of an op amp, and those are called as ideal characteristics of an op amp. We have also seen this part where we discussed about the virtual short property, where when you are considering an op amp with an infinite gain, it's a very ideal case. Your voltages, the voltage difference V2 minus V1 will be approximately equal to 0, or in turn we can say that the node voltages V1 and V2 will be always equal, or they are virtually short even though they are not physically connected together. That is a point what we discussed. And we also discussed about differential and common mode signal, what you understand by a differential signal, what you understand by a common mode signal. In most of the cases, the noise or any common disturbances which affect an IC, which affect any circuit, we represent in the form of a common mode signal. And differential signal, when we say differential signal, the two signals will be equal in magnitude and opposite in signal excursion, or which is having 180 degree phase shift. That is what we revised yesterday. And then we also see very small numerical where how to evaluate the differential gain of this structure. So moving on from here, today we will start, and so the focus of this unit is to understand about the various applications of op amp, right? So I hope you are familiar with this, and we have done the same experiment in the lab as well. So let us start with the very first application of op amp. So as I discussed the other day, we will not be looking into the internal circuit details of an op amp. That is that we will do only next semester. This semester we will consider op amp as a block, or as in block level we will look at that, right? So let us see the first application, which is inverting amplifier, and the regular configuration is we connect a resistance here. The non-inverting terminal is connected to ground, and we connect another resistance in feedback to this, and we call this as R2, this as R1, this as input voltage, and this is your output voltage, right? So what we do here is we'll analyze the circuit considering two things. One is, so what we mark here as A is the open loop gain. So I'm just writing here A as open loop gain. So one thing you can notice here is you have an op amp here, and A is the open loop gain. But in this specific case, especially when you see this as an inverting amplifier, what you can see is the circuit is not in open loop. We have actually resistor connected from output back to input. So for the circuit, if you look the circuit as a whole, the circuit is not in open loop, but whatever we have marked as A is the open loop gain of the op amp. So to make it more clear, whenever you have an op amp, well designed op amp with two input and this output, whatever this gives A, we call it as open loop gain of the op amp, right? Now this in this case, since I have connected from a resistance from output back to input, this works under a closed loop mode. We'll discuss about this kind of this we call it as feedback, and we discuss about feedback later in unit 5, right? So the main intention here is to find the gain, because since this is an amplifier, the main intention here is to find the gain of this amplifier. And I hope you all will know what is the gain expression for this circuit. Can I get a response in the chat? What is gain? So if you're asking the gain, I should write what is the gain here. Gain, what I am expecting here is V out by V in, which is a closed loop gain. This is not a gain without feedback. This is a gain with feedback. So V out by V in. So how will you find this V out by V in? What is the expression? Any idea? Yeah, it is minus feedback resistance divided by, yeah, Sanket and Nishkal, Sai Priya, yeah, all are writing. So minus of feedback impedance by input impedance, that we know. So to find that, what we can do is, we know that the output of an op amp, so let me just mark this node as, say, so far we have marked this as, yeah, V1 and V2. So if I do that here, this is your V1 node and this is your V2 node. And for an op amp, what I know is V2 minus V1 into A will be your V out, right? And when your A is infinity, we can say that V2 minus V1 is equal to 0, or V2 is equal to V1. Now what is V2 here? V2 is 0 in this case. So V1 is also 0, right? So that means this node, which is equal to V1. So if I consider the op amp with infinite open loop gain, or this is the case when your A is infinity, this is the case when your A is infinity, in that case your V2 is equal to V1, and in that case I can definitely find what is the gain expression. How to write the gain expression? Say, since you have given an input signal here, that will give you an input current. Let me mark it as IIN, the input current. That current will be coming to this point, and as we discussed, an ideal op amp will not draw any current, so there is no current flowing towards this inverting input terminal. So this current will flow through this resistance R2. So this will be IN current. Now what I want to measure here is V out. So what is V out? So V out is equal to, if I am writing V out is a voltage from this node to ground. I haven't put any resistors, any load resistance extra I haven't put. So how I can write V out is, can you tell me what is V out in this case? This node voltage is V1, right? So V1 is anyway, it is 0. So V out is basically the voltage drop across R2, right? V out is the voltage drop across R2. This node, it is 0. So let me write in this form, 0 minus V out divided by R2 is equal to IN. Alright, or I can write this as V out is equal to minus IN into R2. Is this clear? V out is minus IN into R2. Now, how can I write this current again in terms of input voltage? Since the requirement here is V out by V in, I can also write what this IN is. IN is this current flowing through this R1. So that can be written as V in minus this node voltage, which is again 0, divided by R1, right? So taking this over here, I can write this as V out is equal to minus V in into R2 by R1, or V out by V in is equal to minus R2 by R1, which is, for an inverting amplifier, the gain for an inverting amplifier is minus of feedback resistance divided by input resistance, and this is when your A is equal to infinity. So this analysis I have done by considering A as infinity, open loop gain as infinity, and this is something what we know. Yes, Partharanjan, yeah, I have seen your response. Now what we are interested is more than this, because this V out by V in is actually the closed loop gain of this circuit, and that closed loop gain is equal to minus R2 by R1. But we are interested to know what will happen when this open loop gain is not infinity, right? Infinity case we already know, at least you know the formula. Now let us also see how this inverting amplifier gain varies when your A is not equal to infinity, or A is a finite quantity. Can you quickly try that and let me know what is the gain when your A is finite? or let me write it here. So what we are going to discuss now is what is the effect of finite open loop gain in the same inverting amplifier. This is what we have seen. I hope this is clear. This part is clear how I derived the gain expression, the closed loop gain for this inverting amplifier, V out by V in, which is minus R2 by R1. The same thing, instead of considering this A as infinity, now it is a finite value. What is the difference? Now what is the main difference here? If this is finite value, then the previous virtual short property or the virtual ground property, what we say, is not valid now. Rather, what we should do is, I'll write the same expression. So now we know that V out is equal to, this expression holds good, right? V out is equal to A into V2 minus V1. This expression holds good, right? Now what is the V2 in this case? The V2 is connected to ground, right? So since A is not infinity, I cannot say V2 is equal to V1. Now what is V2? V2 in this case is equal to 0. V2 is here 0. If V2 is 0, what is V out? V out is equal to minus A into V1, or I can say V1 is equal to minus V0 divided by A. Alright, V1 is minus V0 divided by A. Now the same way how we have analyzed, in a similar way we can write, and we can get the expression for the closed loop gain for an inverting amplifier. Previously we wrote V0 as 0 minus V out divided by the resistance. V out we have written as, first we wrote the current and then we multiplied. In other way how we can write, let us redraw the circuit here, minus plus. Are you guys with me? Can I get some response?
Yes, sir.
Please use the chat window. This is V out. Now this is V2, V2 is 0, but V1 is not equal to 0, V1 is minus V0 by A. Now how can I write V0 or V out? Both are same. I am just using this, this is V out. How can I write V out? V out is equal to, I know this node voltage minus the drop across R2, that also can be written as V out, right? V out is this node voltage. If I know V1, from V1, because the current is again flowing in this direction only, this is plus minus. So from V1, if I reduce or if I deduct the drop across R2, I will get V0. So how can I write V0? V0 is equal to V1 minus the current. So again I consider the current this as, say, the I current which is flowing here. So I can write V0 as V1 minus I into R2, right? Or how can I now write, previously V1 was 0, but now V1 is not 0, it is V0 by A minus I into R2, right? But how can I write I now? So this current, if I write this as I, the same current is flowing through the resistance R2 as well. Both are same current. Previously we marked it as II in input current, the same current only this time as well. So how can I write that current? Since both currents are same, I can write that current as, this node is V in minus, what is this node voltage? V1, V in minus V1 divided by R1, right? Now this is V in minus V1 by R1, or I can further write this as V in minus, here V1 is V0 by A divided by R1, right? Now since I got the expression for I in terms of V in and V out, I can bring this expression back. This I can bring it back and put it here, so that this will be a single equation having only V0 and V in, so that I can derive gain from this expression. So how will I do that? If I write this further, I can write V0 is equal to minus V0 by A minus, in place of I you can bring this equation. What is I? V in plus V0 by A divided by R1 into R2. This is the expression. Alright, now the same thing you can just rearrange. So while rearranging, you will get this as, can you try with me how to rearrange this? V0 by V in Yeah, you can do uh, some rearrangement. So if I do that, V naught plus V naught by A is equal to minus V in into R2 by R1 minus V naught R2 by A R1. Alright, so if I bring this term also to the left side, I can write V naught by V in as minus R2 by R1 into 1 by 1 plus 1 by A plus R2 by AR1. What I have done is I have just taken this minus term also to the left side and then brought in back the rest of the things. I hope you are able to relate this. This R2 by R1 I kept it here itself. Then there are 3 terms with V0. I brought all those terms and kept it in the denominator. This can be further written in this form as V0 by V in is equal to minus R2 by R1 divided by denominator. I'll just take that A common, so it is 1 plus R2 by R1 1 plus R2 by R1 divided by A. This is the expression for gain. I hope this is clear. What we have done is we have taken, first we have looked at op amp as an ideal one, and later we also saw the effect of finite open loop gain. Oh, Sanket, yeah, you have a question. Why can't we use closed loop is equal to open loop by 1 plus beta? Sanket, are you asking for this finite open loop gain or the previous case? Or for this one? So for this one, if I do that again, yeah, if I do that, I don't think we will be able to bring in the finite open loop gain expression over here, right? So as per your question, one second. As per your question, what we know in general is for a negative feedback circuit, the closed loop gain is equal to open loop gain divided by 1 plus A beta, right? This is what we know in general. Yeah, definitely. Yeah, I think we can do that. Yeah, in both the cases we can we can derive this form. In the previous case, what happened is, see, both are same. Actually, both are same. In the previous case, what happened is your A is infinity. When your A is infinity, your AF is approximately equal to 1 by beta. That is the expression, right? When your A is infinity, this is closely equal to 1 by beta. So your gain is in fact your gain is just the beta factor, or the gain is just the what to say, no? The feedback factor in the previous case as well as in this case. Yeah, both are fine. We can do that. The only thing is then we have to find what is a beta, right? We need to get the value of beta, but still we have to do this analysis. This kind of analysis we have to do, because when I'm trying to write the expression to find the beta, then again this node is not at 0. I cannot consider this at 0. I hope, Sanket, is that clear? What you asked? We can definitely do that. But even then you need to bring in, no, because this V1 node is minus V0 by A. So you have to bring in the relation, and we can do that. Yes. Yeah. And another question from Sai Priya, it is, does a closed loop gain mean considering A finite? No, there is no implicit meaning as such. The difference is, see, for any device, for any circuit, if there is an open loop gain, if I am calling it as A, now the closed loop gain is gain with the feedback, right? So as I was writing before, no, A is equal to A by 1 plus A beta. This relation is for any negative feedback system. We can use this relation. It is not with respect to whether your A is finite or infinite. Now if your A is infinite, you can actually approximate this further, and you can write your closed loop gain as 1 by beta, which is only the ratio of, which is the reciprocal of your feedback factor, right? So it is not like in general we say that, no, closed loop gain means always A is infinity. It is not like that. We have to specify whether your open loop gain is infinity or not. That has to be mentioned. Otherwise, we can go out with the, and we can say that, okay, assuming that your open loop gain is infinity, your closed loop gain is equal to 1 by beta. All right. Yeah. So this is what the expression is. Now, if you look at this, the same expression where you have written the finite open loop gain of the closed loop gain of a non-inverting amplifier. Now, what we assumed is A is finite, right? Now, can you tell me what is the case when your A is infinity in this? The same expression, if your A is infinity, what is the closed loop gain again? V naught by V in. V naught by V in is equal to minus R2 by R1. That is what we have derived before, right? So when your A is infinity, the expression reduces back to minus R2 by R1. Otherwise, it is same as this. I hope this is clear. Alright, now for the same amplifier, can you tell me what is the input impedance considering A as infinity? What will be the input impedance? See that the circuit is this, minus plus, this is ground, we have a resistance connected here, this is the feedback resistance, this is V0, this is V in, this is R1 and this is R2. Now the question is, what is input impedance? How will you find input impedance? Input impedance is the impedance How will you find input impedance? Input impedance is the impedance seen from this input side, right? So generally we find by connecting a test, V test, and this current will be I test. So if your A is infinity, can you tell me what is the input impedance? Any guess? R1 plus R2, how it is? Your A is infinity. The moment you say the A is infinity, this node is 0, this node is 0, this is also 0, right? The virtual short is enabled. So this is 0, this is 0, the test voltage what I have connected is just across R1. So in that case, your Rn is equal to, which is V test divided by I test is equal to what? Since this node is at 0, yeah, it is only R1. Yeah, R1 is the input impedance, right? So input impedance is only equal to R1 when your gain is infinity. Now, one more thing what you can comment is, in this case, for your inverting amplifier, your input impedance is, generally I can say input impedance is low, or if you want high input impedance, we have to explicitly put a large resistance as R1 and then consider that as input impedance, right? Yeah. So in general, we can say input impedance is low. Why I mentioned this as low is because usually we use kilo ohm range resistors whenever we work with op amps. Now, if I want to have larger input impedance, we have to explicitly increase the value of R1. All right. Yeah. So now the same thing, so what we have done first is for inverting amplifier, the same thing I am just extending to non-inverting amplifier, and we'll see how non-inverting amplifier is having a difference. So this is non-inverting amplifier. Please post your questions if you have. I am continuously looking at the chat. Yeah, so if you look at the non-inverting amplifier, generally how we configure is like this, minus plus, input is given to the non-inverting terminal, so this is V in, and the inverting terminal is proper feedback is applied, and this is connected to ground, this is R2, this is R1, and this is V out or V0, whatever it is, right? Now, the very first case is, I think, when array is equal to infinity, open loop gain as infinity, so I mark this as A. So when your A is infinity, I can write that V out by V in is equal to, how will I write V out by V in? So you can take in either way. So if I am marking in this this point, if I am marking it as I in, there is no input current here, so the same I in will be flowing, right? So how can I write this again? The same thing, we will write it as, so this node is say V2, this is V1, V2 minus V1 into A is equal to V out for the open loop op amp. So from that, say first if I am considering A as infinity, or V2 is equal to V1. Yeah, Sanket, you have a question for the previous thing? Alright, so here, so when I look at the output impedance of this, so generally how will you find this? We will short the input, then we connect a test voltage here, and then we will find the impedance, right? Yeah, we can say that, because when we short this is ground, it is exactly R2, but with feedback it will be still smaller than that, because it will be reduced by that factor. Yeah, already by looking at the output side you can say that. Yeah, that is true. Yeah, now, yeah, so V2 is equal to V1.